Welcome to lecture 14 of Financial Econometrics. In this lecture, we are going to cover the functional forms. Moving towards the contents, there are different functional forms that can be used while defining our model. So we are going to discuss 4 different types of functional forms. And then basically we are going to understand first what do we mean by functional form, and then we are going to discuss the different types of functional forms. So starting with an example, let's say we have this scatter plot, and scatter plot is simply the graphical representation of our observations. So in this case, for example, this dot represents an individual whose weight is around 12 and whose height is 20. So these all are individuals that are there. So scatter plot gives us an idea of the relationship between the x and the y variable. The y-axis would have our y variable and the x-axis would have our x variable. And if we regress a model, it would give us a straight line that would be representative of this data. And this would be somewhat our model. So we would have a linear model, and if you remember, we had a linear assumption, the first assumption, where we discussed that OLS technique require that the parameters should be linear. Variable can or cannot be linear, it wouldn't matter, but the parameters should be linear. Okay, so in next example, if you see, this is again a scatter plot of the data, but if we draw a straight line, then this might not exactly represent the data. Either the line can be drawn like this or it can be drawn like this. In both the cases, they won't be the representative of the data. So we need to develop a model that represents. So in this case, this model isn't sufficient. This model would draw a straight line like this or this one, depending on the signs. So this model is not representative. So we need to develop a model that represents this specific data. In this case, we will use some kind of non-linear models, although it will be linear in parameters, but it would be non-linear in variable. And if we, so what is functional form? It would be great if we define the functional form. Functional form refers to the relationship between the dependent and the independent variable, the regressant and the regressant. So it is the algebraic form of the relationship. So in this case, to represent this data, we need a line that would be somewhat like this. So this isn't straight, but it represents the data, and this is what we need. And this can be drawn using this equation, this quadratic equation. So in this case, the functional form is have some non-linearity in it. So if we use a functional form that is not the representative of the data, then we would have a functional form misspecification, and that is an issue in our analysis. And in that case, the estimates or the parameters would not be the true representative of our data. So to use the correct functional form, we need to explore different functional forms. This was just an example to give you an idea of functional forms. So let's discuss different functional forms that we have. So we have a log-log model, then we have a semi-log model, then we have a reciprocal model, and then we have a polynomial model. And we would discuss all these models. And the simplistic functional form that we had in our previous example, the left side graph, was the linear functional form, where the relationship between the dependent and the independent variable is graphically represented by a straight line. Okay, so these are different functional forms that we are going to discuss, first starting with the log-log model. So it is called exponential regression model, log-log, double log, or log linear model. And what we would have in this model is that both the dependent variable and the independent variable would be in log form. Now for log, we can either use, we have log and then we have ln, but in this case we are using ln, and this ln represents the natural log that have a power of e, which is a constant 2.71, whereas this log have a base of 10. So in this case, both the dependent and the independent variable would be transformed into natural log. So in this case, B2 is the elasticity between the y and the x variable, and this would be a constant elasticity coefficient. And by constant elasticity coefficient, we mean that it would be same throughout the different values of x. So the important thing that we need to understand is the interpretation of this log-log model. So because both are independent and the dependent variable is in the log form, then we would interpret them in percentage. So we would say that the percentage change in y caused by the percentage change in x. So if we have a model where our dependent variable is the demand and the independent is price, so as the price increases, the demand curve would somewhat look like this. At this point, the slope would be higher. A small change in price would lead to a higher decrease in demand of a product. But at some point, the change in price would have a lesser of an impact on the demand of the product. Say for example, this product is a car. So at this level, the price change, the smaller price change would have a higher impact on its sales. But at this point, say for example, we increase it from here to at this point, the change in demand would be lesser. And it makes sense because if a car is for say 10 million rupees, and its price increases to 10.5 million rupees, then it, for those who are buying this car, would even buy it at 10.5. So a better way to represent, but if we represent it using a straight line, we regress the demand on the price, we would get a straight line, we would have our beta coefficient would be negative. And let's just say the beta coefficient is say 10, and that would mean that every one unit increase in the price, or one depending on the data we have, say the data is in thousands, every 1000 increase in price, the demand of car would decrease by 10 units. But we have already seen that this straight line would not be representative of this data. So to solve this problem, what we do is we take the log of both the demand and the price variable. So we have this demand variable, demand of car, we have different values, and then we have this price variable and we have different values for each demand level. What we would do is we would take the log of this demand values, each value, and we have now a new series, and then we would take the log of this price series and then we would have a new series. And what we do, instead of regressing demand on the price, we would now regress the log of demand on the log of price. Now in this case, let's say we have our beta of, we use the same OLS model, we calculate the slope and the constant term, and let's say the slope was 0.5. So how would we interpret this 0.5, this beta 2 value, the slope value? This is our main objective of this lecture. We need to understand how do we interpret the values when we have different types of functional forms. So in this case, first thing, it would be constant throughout for every different levels of price or x variable. It would represent the elasticity between the independent and the dependent variable. And this 0.5, instead of being interpreted in the units of price or the sales demand, we would interpret it in percentages. So in this case, this interpretation would be for every 1% increase in price, say this coefficient is in negative, the demand of car would decrease by 5%, 0.5%. So now the interpretation is in percentage form. Moving to our next functional form, which was semi-log. In this semi-log, we further have two different forms. We have a log-lane model, where the dependent variable is in log form, but the independent variable or variables are in non-log form. And then we have a lane log model, where the independent variable, where the dependent variable is in a non-log form, but the independent variable, the x variables, are in log form. So the idea is simple, that this part of the name represents the dependent variable and this represents the independent variable. So log lin means the dependent, the y variable, is in log form, and lin log means the independent variable is in log form. So first one is the they are called semi-log models due to some reasons, because as opposed to the log-log model, one part of the equation or one aspect of the equation is in log form and the other part is not in the log form. Okay, starting with the log-lin model, it is the growth model form. So it represents the percentage growth in the y for absolute change in x. Remember, it is log-lin, so the change would be, the change in the dependent variable would be in percentage form in the growth form, whereas the x variable would be in absolute form. So as you can see that the dependent variable is in log form, whereas the independent variable is not in the log form. So for example, the regression of population over time. So it would give us the growth in the population over time. So we expect the population will grow at a constant rate, and this beta term, in this case, in this example, this beta term would represent the growth of the population over time. So we have a relative change in the regressant over the absolute change in the regressor, and the interpretation would be the percentage change in y for units change in x. So that means that if we have a model where our in this case the population is the dependent variable and the time period is in years, then our beta coefficient turn out to be 1.5, then the interpretation of this 1.5 would be that the population would grow 1.5 percent for every 1 year increase, or we can simply put it that each year the population would grow by 1.5%. To give you another example, let's say we have this again income, although theoretically it might not make sense, but just for the sake of this understanding, we have this beta 2 education. So if we have this log of income, then and again the beta turns out to be 0.5, then that would mean, because our education is not in log form, this interpretation would be for every 1 year of increase in education, the salary would increase, because it is in positive, the salary would increase by 0.5%. So the y variable, the y would be in percentage change, whereas the x would be in the unit change. Now, one mistake that I made here is that instead of saying that it would increase by 0.5% or 1.5%, and this is the mistake that we normally make, we need to multiply it by 100. So in this case, the change would be 0.5 into 100, that would be 50. So every 1 year increase in education, the salary would increase by 50%. And in this case, we need to multiply by 100. It would be quite large value, but anyhow, it would be 150. So that would mean each year the population would increase by 150%. So the idea is that there is a relative change in the y variable for absolute change in the regression. This is the first point that you need to remember. And the second point is that you need to multiply the coefficient by 100 to interpret before the interpretation. So moving on to the log-lin model. This is the opposite of lin-log. This is an example of the log-lin model. So we have relative change. This is the same model. Relative change in y is caused due to, I have already explained this. We have this equation, and if the beta is 0.2, then 1 unit change in x would cause 2% change in y. This is what I just discussed. So we need to multiply the beta by 100. So again, in the case of log of wage over education, wage is in log form and education in number of years. So again, we multiply the beta by 100, and we would this interpretation would be for every 1 year increase in education, the wage would increase by 2%. Okay, so next is a lin-log model, and this is the opposite of log-lin model. Here the dependent variable is in linear form, the independent variable is in log form. So we would have an absolute change in y for relative change in x. In this case, you need to remember that whatever beta coefficient you would get, you need to divide that beta coefficient by 100, as opposed to the log-lin model where you multiply it by 100. Here you need to divide it. So in this example, we have food expenditure, and which is in linear form. The total expenditure is in log form, in natural log form, and our beta coefficient is 257. So how would we interpret it? An increase in the total expenditure of 1%, remember the independent variable is in log form, so we would interpret it in percentage form. So if this total expenditure increases by 1%, this would lead to a 2.57. Remember, it is 257, so we need to divide it by 100, and that would give us 2.57 rupees increase. Now you see, the idea is that there is an absolute change in the y variable for the relative change in the x variable. So the independent variable would be in percentages. So 1% increase in the independent variable would lead to a 2.5 rupees increase in the expenditure in the y variable, because y is in linear form. Okay, next we have this reciprocal model. It is also inverse, or we call it reciprocal, and here we have the inverse of the independent variable. The rest is nothing is in log form. So the change in y due to a unit change in the reciprocal of x. So here you just need to keep in mind that this positive value, so this is our variable per capita GNP. Our independent variable is in the reciprocal form, and this is the dependent variable is child mortality. We are studying the effect of per capita GNP on child mortality, and our coefficient turned out to be 27,232. So how do we interpret it? First thing is the sign. This positive sign in case of the reciprocal model indicates the negative effect of per capita GNP on child mortality. So here, instead of saying that when the per capita GNP would, because the sign is positive, so a normal interpretation, if it wasn't a reciprocal model, would be and a 1 unit increase in per capita GNP would lead to an increase in child mortality, but it doesn't make sense, right? When the per capita GNP would increase, there would be more spending on health, and health facility would become better, and the child mortality would decrease. So this, in case of reciprocal, the sign should be inversely interpreted. So in this case, the 1 unit increase in per capita GNP would decrease the child mortality. Okay, last one on our list is the polynomial model, and we had some discussion over it in our first slide. So this y is regressed on a number of variables. So there isn't one variable. Now we have multiple regression model which are higher power of the same variable. So in this case we have x and then we have x squared, so higher power of the x. So in this case, this is our quadratic equation, but it is not necessary that the equation would always be quadratic. It can be a cubic form. So in case of quadratic equation, it would be called a second degree polynomial. In case of cubic, it would be called a third degree polynomial. So when our data represents a concave or convex shape, then in that case we would have a peak, and in the another case we would have a trough. It would be a U or inverted U shape scatter plot. So in this case, these type of models are represented by quadratic equations. We can have multiple peaks and troughs. So this kind of model where we have a peak and then we have a trough would require would have a cubic form. So we would have three independent variable x, x square and x cube. So if this is how our data looks like, then we need to use the polynomial model. We need to use a quadratic term. So if this beta 2 is greater than 0, that is in positive, and this beta 3 is less than 0, this quadratic form is less than 0, then that would mean we have this kind of data where this beta 2 would represent this part of the data, and the beta 3 would represent this part of the data. And if it is opposite, we have beta 2 less than 0 and beta 3 greater than 0, then it will represent this kind of a graph.